Theovis, the idea made visual.
London, 1854. Cholera is killing people, street by street, and a doctor named John Snow tries something simple. On a map, he marks a dot, then he asks one question. For each death, which water pump is the nearest? The dots pile up around a single pump on Broad Street. He has that pump shut off, and the dying stops.
Wait, he cracked a deadly outbreak just by asking what's closest to what?
That's the whole idea. Your phone uses it to pick a cell tower. Games use its twin to build the mountains you walk through. So let's actually build one. From scratch, watch what happens. Here they are, 7 dots. Think of them as 7 height markers dropped on a hillside. Everything for the rest of this video happens to these exact 7. Our whole job is one question. Which dot do we join to which to cut this into triangles?
Feels like there can't be that many ways to connect 7 dots.
More than you'd think, and most of them are terrible. Let me show you a terrible one. Watch. Join every dot back to this one corner. Technically, it's triangles, but look at them. Long, thin splinters. We call these slivers, and a sliver is poison for a computer. The light glitches across it, textures flicker, and the math one sliver can wreck the whole.
So the goal isn't just, it's make no slivers.
Exactly. Fat triangles everywhere. Now, how does a computer know a triangle is fat without measuring a single angle? Here's the trick. Any 3 dots fix exactly one circle through them. Take a nice fat triangle from our set. Draw its circle. It's clean, empty, nothing else inside. Now, take one of those slivers. Draw its circle. It's huge and flat, and look, a neighboring dot falls right inside it. That's the tell. Just a fat triangle, empty circle. Sliver, crowded circle.
So is this triangle good becomes, is it circle empty?
And that single rule, every circle empty, is the whole of Delaunay triangulation. Keep every circle empty, and you automatically get the fattest triangles possible. Same thing, 2 faces. And a computer checks is this dot inside that circle without ever drawing the circle. It drops the 4 dots into a little formula, just multiplies and adds, and reads the sign. Positive, the dot is inside. Negative, it's safely outside. No circle, no square roots, just fast, exact arithmetic.
So the whole rule is the sign of one number. That's why it runs in real time.
That tiny check is the atom everything else is built from. Let's use it to fix a mistake. Take 2 triangles in our mesh that share an edge. They make a little 4-sided patch. Right now, the line splits it the wrong way, and the check says the opposite dot. So flip it. Erase that line. 1 line out.
And because empty circles mean fat triangles, the flip can only help. The skinniest angle gets bigger.
So keep flipping every illegal edge. When there's nothing left to flip, you're done. And here it is, the finished mesh for our 7 dots. Every triangle fat. Watch. I'll draw the circle for each one, and not a single dot is ever trapped inside. This is the best way to connect these 7. And one simple local rule found it.
No slivers anywhere. And we never had to check all the billions of other options.
That's the magic. One local rule, applied everywhere, gives the globally best mesh. Now a player walks closer. Right here, we don't rebuild everything. Watch. Ask which existing circles this new dot falls inside. Only these few go bad, and they sit together in one little patch, the cavity. Delete just that path. It leaves a clean hole. Now, fan the new dot out to the edges of the hole. Done. Delaunay again, and we only touched the neighborhood.
So the terrain rebuilds itself around me as I move, without ever freezing up.
That locality is exactly why open worlds feel seamless. And this isn't a one-time thing. As you walk through a game world, new detailed dots. Watch our traveler cross the terrain. And every time a dot appears, the mesh right around it rebuilds itself.
So the ground is literally being re-triangulated as I walk. Every single step?
Every step. That's how a huge open world stays crisp under your feet and cheap in the distance at 60 frames a second. Remember Jon Snow's nearest pump map? Watch it appear on our own dots. Give each dot the ground that's closest to it, and the plane splits into territories, the Voronoi diagram. And it lines up perfectly. Two dots share a triangle edge exactly when their territories touch. Our mesh and these territories are the same information twice.
So the map that found the cholera pump is literally the flip side of the mesh we just built?
One idea, that twin is how a game decides who owns which ground and where an eye can walk. Now the payoff. Remember, each dot had a height. Lift them. The flat mesh tilts up off the page and becomes a little hillside. The same triangles, now in 3 dimensions. Nobody sculpted it. It's 7 dots plus 1 rule.
That's a tiny hill, though. A real mountain needs way more than 7 dots.
So we scale up. Same rule, just thousands of dots instead of 7. There it is. Thousands of height dots, wired by the exact rule we just learned on fly down close, and you can see it's all triangles, every one obeying the empty circle rule, so the light stays calm and the surface never tears. This is the mountain you walk across in a game, and it's the same idea running on fluids, on breaking walls, even on the face scan that unlocks your phone.
From 7 dots to a whole world, and it never changed the rule once.
Same 1934 rule, all the way up. So hold the one idea, every circle empty, every triangle as fat as it can be, and the exact twin of the nearest neighbor map that once stopped an epidemic. Not 3 tricks, 1 theorem, and that is how 7 dots become a mountain you can climb. If you want to go deeper, here are the sources this rests from Delaunay's own 1934 paper to the modern algorithms that put it inside your favorite game engine.
If it finally clicked, subscribe. It really helps. And I'll see you in the next one.